On June 26, 2026, the ground beneath the southern Philippines split open with a force strong enough to level buildings. And for 3 days, seismologists have been asking the same question. Was this the warning shot? Not a metaphor, not a headline exaggeration, a literal physical shock wave that traveled through solid rock at over 3 miles per second, and it originated from a fault system that scientists have been watching with growing unease for over a decade. The number that matters here isn't the magnitude, it's what comes next. To understand why this earthquake has seismologists on edge, you need to understand where it happened. The Philippines sits at one of the most violent tectonic intersections on the planet. 4 major plates grind against each other beneath this archipelago. The Philippine Sea Plate, the Eurasian Plate, and 2 smaller but no less dangerous microplates caught in between. Running straight through the middle of this collision zone is the Philippine Fault System, a nearly 1,200-kilometer-long fracture that cuts diagonally across the entire country, from Luzon in the north to Mindanao in the south. This isn't a single fault, it's a network. Dozens of interconnected segments, each capable of rupturing independently, and each one close enough to the next that a break in one can transfer stress into another. For decades, scientists have mapped these segments, measured their slip rates, and calculated how much strain has built up since each one last ruptured. Some of these segments haven't moved in over a century. That strain doesn't disappear, it accumulates, and it waits. The Philippines records thousands of earthquakes every single year, most too small to feel, a handful large enough to make headlines, and a rare few that force scientists to reassess everything they thought they knew about a fault's behavior. Before this week, the southern segment near Sarangani had been quiet enough that some assumed the risk there was lower than in the north. That assumption just changed. And it's worth asking, if a segment considered lower risk can produce a magnitude 6.5 rupture with almost no warning, what does that say about the segments considered high risk, sitting dormant directly beneath a capital city of 13 million people? At 11:34 UTC on June 26th, the ground 34 kilometers southwest of Sarangani ruptured at a depth of 42 kilometers, releasing a magnitude 6.5 earthquake. Maximum shaking intensity peaked at MMY 7.0, classified as severe. The United States Geological Survey confirmed the event within minutes, and citizen reports began flooding in from residents who felt the ground move beneath them. This wasn't a deep, distant tremor that dissipated before reaching the surface. It was shallow enough and strong enough to be felt across a wide radius. And shallow earthquakes are precisely the ones structural engineers fear most, because the energy has less distance to travel before it hits buildings, roads, and people. What makes this event different from routine seismic activity in the region isn't just the number on the Richter scale, it's the location. This section of the fault system sits uncomfortably close to segments that feed directly into the broader Philippine fault network. The same network that runs beneath Metro Manila. In the hours after the quake, disaster response teams moved through affected communities checking for structural damage, downed power lines, and blocked roads. Early reports described cracked walls, collapsed masonry in older buildings, and residents who spent the following nights sleeping outdoors, unwilling to risk aftershocks, bringing down what the main shock had already weakened. This is the pattern seismologists watch closest, not the initial rupture, but what the ground does in the days that follow. Here's where the story stops being about one city in Mindanao and starts being about 13 million people. If a rupture like this one occurred on the Valley Fault System, the branch of the Philippine Fault that runs directly beneath Metro Manila, the outcome would not resemble what happened in Sarangani. Government disaster models built years ago, using data from the Philippine Institute of Volcanology and Seismology, project that a major rupture on that fault could destroy tens of thousands of buildings and leave hundreds of thousands of people without shelter in a matter of seconds. This is not speculation. This is the scenario planners have been preparing for since before some of you were born. What if the next major slip isn't in Sarangani, isolated and survivable, but on the segment that cuts through the most densely populated metropolitan area in the country? Emergency planners call it the big one, not because it's guaranteed, but because the fault is real, the strain is measured, and the history of the region shows these faults do eventually break. If a major rupture strikes during rush hour, when highways are packed and buildings are at full occupancy, the damage compounds in ways that are difficult to model. Bridges connecting the capital's districts could become impassable. Water and power infrastructure, already strained by daily demand, could fail across multiple districts simultaneously, complicating rescue efforts exactly when they're needed most. Stop for a second. Let that sink in. This isn't a hypothetical volcano someday erupting. This is a fault line that has already ruptured before, sitting beneath a city that has grown by millions of people since the last time it did. To understand why this keeps happening, you have to understand what a strike-slip fault actually does. Imagine two enormous slabs of rock pressed against each other, not moving apart or together, but sliding sideways, like two conveyor belts running in opposite directions, but jammed by friction. Energy builds at the points where the rock is locked together, the same way pressure builds in a stretched rubber band. That energy doesn't release smoothly. It releases in sudden, violent snaps once the friction holding the rock together finally gives way. That's what happened near Sarangani. The rock had been locked for years, storing strain, until the accumulated stress exceeded what the fault could hold, and it broke. The unsettling part is that stress transfer doesn't respect segment boundaries. When one section of a fault ruptures, it doesn't just relieve pressure locally, it can redistribute that stress onto neighboring segments, effectively pushing them closer to their own breaking point. Seismologists studying the Philippine Fault System have documented this exact pattern before, in sequences where one rupture appeared to trigger another months or even years later on a completely different section of the same fault line. This is why scientists rarely treat a single earthquake as an isolated data point. Each rupture is read as a message about the state of the entire system, a system that in this case extends hundreds of kilometers north to the exact fault segment sitting beneath the nation's capital. This is where the story stops being about seismology and starts being about the 13 million people who wake up every single day directly on top of this system. Metro Manila is one of the most densely populated urban regions on Earth, and a significant portion of its buildings, including hospitals, schools, and government facilities, were constructed before modern seismic building codes were strictly enforced. Disaster response officials have spent years running earthquake preparedness drills specifically because of this fault, training residents to expect the ground to move without warning. These drills simulate mass evacuations, hospital surge capacity, and the collapse of key transportation corridors, because officials know that in a worst-case rupture, the first 90 minutes will determine how many lives are saved. A structural engineer who has studied the Valley Fault System put it simply: it isn't a matter of if this fault ruptures, but when, and the region's disaster planning treats that as an operating assumption, not a distant possibility. To put the scale of exposure in perspective, 13 million people is more than the entire population of Sweden, living, working, and sleeping directly above a fracture in the Earth's crust that has already proven, this week, that it is far from dormant. So what happens now? Seismologists at the Philippine Institute of Volcanology and Seismology are closely monitoring aftershock patterns near Sarangani, watching for the specific signature that would indicate stress is migrating toward other active segments. The number they're watching isn't the magnitude of the last quake. It's the rate and pattern of the aftershocks that follow, because that pattern often reveals whether a fault system is settling down or building towards something larger. Nobody can predict the exact day a major earthquake will strike, but the Philippine Fault System has shown, once again this week, that it is active, it is loaded with stress, and it runs directly beneath one of the most populated cities on the planet. The answer to whether Sarangani was an isolated event or the opening move in something larger may come sooner than anyone expects. Subscribe to stay ahead of what's coming.